Okay, good morning. I'm DK Panda from Ohio State University. So today I'll be talking about the future of MPI. So please feel free to ask me questions. I'll also stop in between. So broadly I'll be covering the following topics. First I'll try to give a broad overview of what is happening on the PetaFlops and how we are moving into the ExaFlop systems, what are the kind of challenges remaining there, and then I'll try to give you a brief overview of the programming models being used for these systems, and especially on MPI, what has happened in MPI 1, MPI 2, and then currently we are working on MPI 3. And then trying to go into some of the overview of the MPI 3 features. So this is MPI 3 is the new standard, so I'll be talking a little bit of that. And then I'll go into a little bit more details onto the MPI project we have been working at OSU called the MVAPICHZ and MVAPICHZ2. Many of you might be familiar. And I'll try to address some of the issues what we are considering so that we can continue to scale MPI on the modern systems and then move to the Exascale systems. And then finally I'll be concluding. So some of you might have seen this chart. What this chart is from the top 500 list. So what it shows that these are the years and this is the overall performance. This line is actually the number 1 system. Okay, and this line is the number 500, that is the lowest system in that top 500, and then this is the cumulative one of all the machines. So this shows very nice trend over the years. Here if you see, like, we have been going in a stepwise fashion, and then this is the June 2012. Now we have crossed 16 petaflops, so this is the IBM system at Lawrence Livermore National Lab. And so now if you see, like, the next thing what we want to do, like the 100 petaflops, and this is what people have been talking, mostly like by 2015, in another 3 years, might be we'll reach that stage. And then a lot of discussion is taking place with respect to ExaFlop. And originally it was targeted for 2018, but now I think people are thinking 2019, or it might go into 2020, 21. It all depends on the budgets and all different countries, how much money they are trying to pump. So we may see a little bit of flexibility in this to have an ExaFlop system. So now this kind of roadmap, here if you see, also looking at a little bit in the past, you will see that amongst all these systems, the clusters are playing a big role. So here it shows like, let's say in the November 1996, there were no clusters in the top 500, only like these were the traditional MPP systems. But now over the years, if you see, it has gone almost to the 80%, almost for the last 5 to 6 years, it is hovering around 80, 82, 83% kind of things. So that means from all the top 500 systems, the clusters are playing a big role, so we need to keep an eye on that. And of course, within that clusters, InfiniBand is also getting a big momentum. So here we see like almost 209 clusters in the latest list, almost close to 42%. And just on the top 40 itself, like 13 systems, like starting from here in the Germany, 147,000 to all the way from China, and then France, and then also in the US. So it is becoming very common to actually deploy this kind of 100,000 core systems with InfiniBand. So these clusters are actually gaining a lot of momentum to become also strong players in the Exascale world. So with respect to this now, so these are the kind of clusters or deployments are taking place, but now the thing is how these machines are being programmed. Of course, we need a programming model to program these systems, and this is what I'll be talking a little bit on the overview of the programming models, and especially MPI. Now, if you take a look at the programming models, of course, the programming models provide an abstraction for the machine model, so that means how the data is distributed, how the processes are distributed, and how the computation takes place. And broadly, you can see like 3 different models here. So one is of course the shared memory. That means every processor, the memory is being shared across all the processes. And then here is the distributed memory, that is the MPI, or the message passing. And then there is a new one which is coming, and I'll be talking a little bit later on that, called PGAS, or Partition Global Address Space. So here the idea is that here it is like they have the memory, but these are logically shared. So it is not like here these are like cache coherent shared memory kind of environment, but here it is a logically shared. So in that way you can actually try to scale the systems with shared memory abstraction. And that's what actually a lot of people have been thinking to head towards the Exascale systems. So some kind of an hybrid programming from MPI and then PGAS, and I'll also be talking more on this a little bit later. So if some of you might have already programmed using MPI. How many of you have used MPI? Okay, some of you. So, probably is a message passing library which was standardized by the MPI forum. It's like you can write programs in C, C++, Fortran kind of things. And the goal is actually to have a portable, efficient, and flexible standard for writing parallel applications. And of course, this is not an IEEE standard or an ISO standard, but it is widely considered like an industry standard for HPC applications. So prior to 1994, what used to happen is that a lot, I think it's getting cut here, okay. So especially prior to 1994, every machines, whatever was coming, like the large scale machines, they had their own programming models. Okay, so then what was going to happen is that if you buy a machine, you can only try to write your parallel application using that software environment, whatever that machine provides. Okay, so tomorrow if the machine changes, then again you have to rewrite your application. So in that way, the machines are not becoming very portable, or your application was not portable. So this is where actually there was a forum started with the combination of all different industry and then the national labs, and that is where called the MPI forum. And then they actually tried to standardize in 1994 MPI 1. Okay, so that's like the MPI 1 standard which came into picture. And then very quickly in the next 2 years, people saw that the primitives or the mechanisms or the APIs which were provided in the MPI 1 was not good enough to write more sophisticated parallel applications. So then people moved to MPI 2 that was introduced in 1996. But then you will see that almost for 12 years nothing happened. People were very happy. MPI 2, whatever was available, people were able to write programs and then really get the scalability and performance. But then again, a new kind of requirements came, and people saw that now it's the time to actually revise the MPI standard to have newer kinds of features and newer kinds of mechanisms, and this is where the MPI 3 started. So this work has been going on almost for last 4 years. 2008 it started, and it is continuing. So in fact, in the next week at the Euro MPI in Vienna, actually the MPI 3, the final version is being voted on. And if that voting passes, so it will be the MPI 3.0, which will be coming out, and it will be very formally announced at the supercomputing conference in November. So the major MPI features, what it means, if those of you would have written parallel applications with MPI, it basically provides a very standardized way to do point-to-point communication. So that means from a process to another process, it could be within the node or it could be across the node. So how do you really try to send the messages? And it has two versions, like one is the two-sided communication. So that means I'm trying to send and you are trying to do the receive. And it also has an one-sided communication. So that means instead of like doing a send and receive, you can actually do a put. So that means one process can actually try to write the data to the another process memory, and then on the other way you can also do a get. So that means you go and then read it from the other process memory. And the other one, which is the communication, which is very big in the API and puts a lot of focus on the performance and scalability. I'll be talking a lot about that. Is called collective communications. So these operations are basically, as the name suggests, collective. So that means not just only one process participates, but a lot of processes participate. So let's say you want to do a broadcast. So that means you are trying to send the data from one process to all the processes. Or if you want to do all to all, that means every process has some data. You are trying to exchange the data or try to do reduce, all reduce. So like this, a lot of operations are there which are called collective. And also there is like you need to do some kind of a job startup. When you are actually trying to initiate the job, it has to actually go to all the processes before it gets started, and also it has parallel I/O. So all these are like the major kind of features we see in the MPI. Now if you take a look at all these kind of standards, let's say MPI 1 or MPI 2 or MPI 3 or PGAS, you name any of those kind of environments, there is a standard, but how do you really design the communication libraries for those standards? Okay, so that becomes the biggest challenge. So here it is like an animation I'm trying to show. So at the very bottommost you will see we are trying to write these commodity computing systems. It could be all kinds of multi-core environments. Now we have accelerators, NVIDIA GPUs, all these are coming. So then we have all the commodity networking technology. It could be the Ethernet world, or it could be the InfiniBand world, or it could be even the Rocky world. So all these different kinds of networking standards and protocols are coming. And then at the top, you have the applications, the end applications, or the libraries, or even the middleware. So now, of course, we want to have some kind of an environment here so that it takes the best features and performance here and then delivers to these applications. And then these applications are typically written, as I mentioned, with some kind of a programming models. It could be MPI, it could be sockets, or it could be like PGAS. I'll be talking a little bit more on that, UPC, OpenSMEM, etc. So the broad challenge then lies, how do we design these environments? And then here you will see that this is the standard library or runtime which comes into the picture. So that means you can have an MPI runtime, or a library, or a runtime to support hybrid programming models. And inside that, you need to focus a lot of these things like point-to-point communication, collective communication, synchronization, I/O file system, QoS, and fault tolerance. Okay? And this is how, if you try to put things together, and especially if this runtime is trying to be designed in a portable manner and being linked to the MPI, so any kind of environment comes in, you have to provide these additional features to go through this runtime so that the applications or the end libraries can actually take advantage of that. Okay, and I'll try to go into a little bit more details of that to illustrate how some people can design this kind of stuff so that in the end you get the best performance at the applications level. Now let's take a look at the Exascale system. So let's say we want to design MPI library for the Exascale systems. So this is again, this figure has been taken from a DOE Exascale study led by Professor Jack Dangara. You can see on the web, you can find out an Exascale report. And here you will see that what this tries to do is like it tries to bring out different metrics of the systems, like what should be the system peak, power, memory requirement, node performance, node memory bandwidth, node concurrency, total node interconnect bandwidth, system size, concurrency, storage capacity, I/O rates, mean time between failures, etc. Now, interestingly, what happened is when the study was taking place, so that was 2010, and that time the target was 2018. So what it says is what exists out there today, and what is going to happen in 2018, and by what factor there will be a difference. Okay, so that shows like which dimension or which metric will be very significant, and especially we'll try to focus on these 4 parameters, and that shows like how the systems are going to be changed over the years. And here if you see like node concurrency, so that means the number of cores within the node. So in the 2010 they were around like 12, and now of course like 36, 48, even 64 cores per node we are having, and people are predicting like in the 2018 or 2020 it will be 1,000 or 10,000 cores will be there per node. Okay, so that itself will be like almost 100 to 1,000 factor improvement. Then at the same time, the total bandwidth which will be going out from the nodes, here it is around like 3.5 gigabytes per second, but there will be like almost 200 to 400 gigabytes per second will be there, the data which is going outside from a node. And then the system size, which is the total number of nodes, not just cores. So here it was around like 18,000, and people are predicting that in the Exascale system it will be 100,000 or a 1 million number of nodes will be there. And the final thing is the total concurrency. So that means how many threads or how many processes you should be able to run. So here it is like a 225,000, and here people are thinking of a billion kind of degree of concurrency you need to achieve. So here almost it is like almost a 10,000 factor improvement. So these are the kind of big challenges what the community is looking forward to really go for the Exascale system. So in that context, now what are the broad challenges? I mean, those are all the metrics, but the broad challenges, this study was done by a DARPA Exascale report by Professor Peter Foggy. So he broadly provided these 4 challenges. One is the energy and power challenge. Okay, so that is the biggest factor, which is actually, in fact, putting a lot of constraints on bringing out these exascale systems, like how much power is needed. Okay, and this is the power comes because of the data movement, like the data is being moved, and this is where a lot of power goes. And in fact, in the previous slide, if you saw here, I didn't put it in a highlight. What people are predicting is only 20 megawatt. This is how they want to design the exascale systems, that only it will take 20 megawatt, and that is putting a lot of pressure on all different architects and the designers in the industry to bring out all these components so that we can make actually an exascale system which is practical. And then it also provides memory and storage challenge. That means it's very hard to achieve high capacity and high data rate. And as I mentioned, the other challenge is concurrency and locality challenge, because when you are thinking of billion of threads, how do you keep all the threads busy? So that means you need to invoke all kinds of mechanisms for prefetching, for caching, all kinds of those techniques need to be used to keep all these billion threads busy. And the final challenge is the resiliency. So that means when you are trying to design this kind of systems, obviously there are so many components and failures will occur. So how do you really take these failures into account so that make the machines operational? So in that kind of keeping that kind of overall view, now we need to see like what is MPI is doing. Now MPI has been a dominant programming model. It has been being used by all the systems, and of course people will continue to use MPI. So that means we need to think that how the MPI can be extended for exascale systems. So here there are like a few of the points what the MPI forum has been talking, and again the main thing is that if the power is required for the data movement, so how do you handle it within MPI? So one of the important discussions which is going on and will be part of the MPI 3 standard is the non-blocking collectives. Okay, so in the beginning, yes.
Is that already part of MPI 3?
Some of these,
you come to this.
Yes.
You know, what is part and what
yes,
is not.
yes. Next set of slides will come. Okay, this is like I'm going very up and then I'll go in.
Yeah. Okay.
So the non-blocking collective, so the idea here is that the collectives, as I indicated, like it actually involves all kinds of, all the processes. So let's say you are trying to do an all-to-all or a reduce or all reduce. So far the standard only provides blocking collectives. So that means if I'm participating, all the processes are trying to do all-to-all, unless the all-to-all finishes, no process proceeds. Okay, and this is where actually we see a lot of performance bottleneck and things don't scale. So what this is trying to do is trying to make those collectives non-blocking. So that means we can initiate all-to-all, but we don't have to wait for the results to finish. And provided if we have some redundant computation, or let's say computation from the previous iteration, that can continue while the collective is going on. Okay, so then we can try to really achieve overlap between the computation and the collectives, and that will try to provide good performance and speed up. And the next one is the one-sided operations. So I mentioned that MPI 2 has some get and put operations, but I'll show a little bit later that it has some limitations. So then people are trying to come up with a better standard so that you can actually do these kind of get operations or put operations with reduced synchronization and sender at the receiver. And to manage this concurrency, which is the biggest issue, people have been thinking, like if those of you who would have written parallel program using MPI, you will see that MPI is good for regular communication. So that means if you have data distributed and if you know the communication pattern, it is very easy to write parallel program using MPI. But let's say your application is irregular. So that means you do not know the data movement, okay, or it is very imbalanced. Load balancing is not there, then it is very hard to write MPI program with good performance. And this is where people are thinking that how we can try to move into the PGAS, or is it a UPC or global arrays or OpenSMEM, those kind of PGAS models, because the address space is shared, then it becomes much more easier to write parallel program. So people are thinking actually the hybrid. That means you can write for your application, if you have a regular communication pattern, use MPI. If it is irregular, then you use the PGAS. And it can be hybrid. You can actually write some parts of your application using MPI and then some part using PGAS, and then you will get good performance. In fact, I'll show you some performance numbers towards the end. And finally, there is resiliency. So how do you really detect the failures? How do you manage failures? So these days you see MPI, for example, if something, a process fails, the job totally aborts. So now the thing is how you can try to keep the job alive, and then if there is some redundancy or if your application, you can try to recover. So all those kind of issues are being discussed. So with these are the very high level models. Of course, these are a lot of demanding topics. So what MPI 3 tried to do is try to handle some of these things in the standard. Okay, not all. And as I mentioned earlier, like the MPI 3 started in 2008, so almost 4 years of discussions have taken place. So in fact, some of these people have reached consensus, some of the others they didn't reach consensus. So that's how the MPI 3, whatever will be coming out, MPI 3.0 in the later part of this month and the next month, only has some set of features, not all. And the plan is to have MPI 3.0 out, and then people will be talking MPI 3.1, 3.2, or MPI 4. So those are the kind of things which will happen in the future. So in MPI 3, the three important thing which is coming out is the non-blocking collectives, improved one-sided model, and then MPI Tools Interface. And this is what I'll be talking a little bit more in detail. So there is already a draft version available. So in fact, yesterday in the evening there was a cutoff. So the committee has discussed, everybody has contributed. So the final draft is available. If you go to that site, you can take a look at it. And as I mentioned, the next week is the Euro MPI conference, and then they are trying to actually vote on this. And then if it passes by the MPI forum, so this will become the MPI 3.0 standard. So I talked a little bit about the non-blocking collective operations. So broadly, it enables the overlap of computation and communication, removes synchronization effects of collective operations. But now there is already like collectives which are blocking. Okay, they don't want to throw it out. It will still be there, and then the non-blocking is being added. So that is adding to some confusion, and this is how the standard outlines the solution. So broadly, it says like completion when local part is complete. So that means, let's say you are trying to do all to all. You have pushed your data, so that means you can say that I am complete with respect to that operation. I might not have received all, but I can proceed with the computation. The completion of one non-blocking collective doesn't imply completion of other non-blocking collectives. Okay, so you can have like multiple concurrent collectives going on. There is no tag for the collective operations, and that means you can actually introduce many non-blocking collectives, but then you have to worry about in the implementation to ensure that there is like all these non-blocking collectives actually finish with the proper data. And the non-blocking calls do not match blocking collective calls. So that means MPI implementations may use different algorithms for blocking and non-blocking collectives. So therefore, they may not, the non-blocking collectives cannot match the blocking collectives. And the broad idea here, I think this is what matters to the end users. The blocking collectives so far, they have been optimized for latency. But as the definition of the non-blocking collective says, we want to overlap computation with the collective. So that means these are the things which needs to be optimized for overlap. And then users must call also collectives in some order of all ranks. There are some progress rules. So these are important for the library designers. As the end users, you need not focus a lot on these. You can just call from your application like these kind of semantics, like MPI-XI barrier or MPI-XI already used. So just like the point-to-point, you have an I send and I receive, which are non-blocking send and non-blocking receive. Similar kind of semantics have been given for non-blocking collectives. So take a look at like some of the one-sided communication. As I mentioned earlier, the one-sided communication provides a way for different processes to talk to each other using get and put kind of communication models. And this is easy to express irregular pattern of communication. So that means if you take some memory from each process and then try to create a window, this rank 0 can write here, rank 2 can read here, or rank 3 can put the data, rank 1 can read. It becomes much more easier to write applications. And here, the idea is to decouple data transfer with synchronization so that we can achieve better overlap of computation with communication. Now, MPI 2 already had like this kind of one-sided communication. So here, it had like the processors, there is a private window, there is a public window, then you can have incoming RMA operations coming here, then there were some synchronizations, and then you do some local memory operation. Now the broad difference is here, like MPI 2, it was targeted for non-cache coherent systems. But in the MPI 3, now they are trying to expand that and then they are trying to provide here some unified two types of windows, unified and separate, and then also the unified window leverage hardware cache coherence. Okay, so those are the kind of changes which have come into play. And here they provide a lot of different kinds of RMA calls. I don't want to go into all the details, but it provides some flexibility in semantics, like how do you actually create the window in a dynamic manner, how do you allocate, how do you do the operations, put, get, and accumulate, fetch and add, compare and swap. These are the kind of atomic operations which are provided. You can also do some locking. You can do your window plus all, window plus local or local all. You can also do window synchronization. And then there were some erroneous states were there in MPI 2, but they are being undefined in MPI 3. So broadly, they are trying to make it much more easier in the MPI 3 to use this remote access or the get and put model so that people can write, the library designers can implement these with low overhead, and then the application writers can actually take advantage of these to write effective parallel programs. So that is the kind of goal. The final thing which is coming is called the MPI Tools Interface. Now, prior to this, if you remember, like most of the time, there is only one common interface people have been using called PMPI. Okay, so it's like a profiler interface which is out there. So many times, let's say you are a library designer, you put a lot of internal features, like saying this is the buffer size or this is the number of parameters. Okay, and it becomes very hard for the end users to find out what is going on in the library. And it also becomes very hard for the tools people to write specialized tools to know what is going on within the MPI library. So now MPI Forum has come back with a much more standardized way to do it, and this is what they call MPI T. So for example, internally, let's say you have some eager limit, like the eager versus rendezvous protocol, MPI library implements. So what is the buffer size, what is that limit, what is the time is spent in blocking memory usage, what is the, like, how many packets are being sent, what is the threshold. So all these are like inside library information can be actually passed to the upper layer. Okay, so if you have a good tools, then the tools designer actually can extract this information and then give it to the user. Okay, so that is the kind of like the feature which is coming in the MPI. And then there are a lot of kind of minor features which are going here. So I have just provided a list. Some new Fortran bindings, non-blocking file I/O. They removed the C++ bindings here. Support for large data counts. Now there is a collectives also. There is a new thing which has been introduced called scalable sparse collectives. So that means in the collectives, earlier I said all the processes need to participate. That is no longer there. So there are new kinds of collectives being introduced. Only a subset of processes can participate. So that is called sparse collectives. Then there are some distributed graphs, topology aware communicator creation. I'll talk a little bit about this in the next few slides. Then I talk like non-collective communicator creation, some enhanced data type supports. Then there is a hybrid programming support and numerous cases. So this is how actually the MPI 3 standard which is coming up. Any quick questions here before we move? Yes.
Yeah. You know, we probably have a more general discussion on MPI 3, but what does it mean that the C++ bindings have been removed from the standard? You know, you have new Fortran bindings, but you say you removed the C++ bindings. What does that mean?
Yeah, so there were like different kinds of controversies here. Like, it's not like earlier, like people had provided some ad hoc way to have C++ binding. Okay, so now what they're saying is not that you cannot use C++ binding. It is just being removed as a part of the standard. Like, not that you need to do it in a particular manner. It still supports, it's just a flexible manner. Okay. Any other questions? This side people are still sitting. You have taken coffee? Everybody is awake? Okay. Any questions? Okay. So that gives a broad overview, and now let me tell you, go into a little bit more detail, saying, okay, these features are there, so how do we really take advantage of, or how do we design these kind of things, and what kind of performance issues come? So in this context, I'll try to introduce the MVAPICHZ project, which we have been working almost for the last 12 years, if some of you are not familiar with this. So we started this project in 2002, almost like when the InfiniBand came into picture. We had MVAPICHZ, which is the MPI 1 standard, MVAPICHZ 2, which is the MPI 2.2. And in fact, last week we made a new release called MVAPICHZ 2X. And this is actually supports the hybrid programming, MPI plus OpenSMEM. That is the release we have done, and we'll be doing MPI plus UPC plus OpenSMEM very soon.
Acronyms and names are getting longer and longer. So, what does MVAPICHZ? You know, I'm familiar with MPICH, but MVA, what does it stand for?
Yeah, so this is it's an extension from MPICH.
Yeah.
Okay, so in fact the name actually says it's MVAPICHZ. So we took the MPICH, we took the MBICH. There was a version called MBICH from Lawrence Livermore Lab, and then we tried to combine it. And broadly, in the beginning, if you read it properly, try to capture there is a VAPI here. If those of you are familiar, InfiniBand had the VAPI interface, like the Mellanox VAPI and all, verbs interface, and that's what the name stands for. But of course, the verbs have been changed, the VAPI is no longer there. It has moved to the open fabrics, but still it captures, that name captures MPICH, MBICH, VAPI, and MPI. So everything is together in that name. Okay, so that's how it says that it is targeted for all these environments. And over the years, like this has been being broadly used. Like so far, there are more than 1960 organizations in 70 countries are using it. People can download from our site, or it is integrated with a lot of other software stacks. And this is also empowering a lot of top 500 clusters. So these are the type of clusters, very large clusters. When we started in 2002, we just had the initial MPI only running on like 2 nodes, but now it is running almost like 100,000 core systems in an easy manner. And more importantly, like we are working with, this is a new system which is coming out, if some of you are familiar, the NSF tag system, Stampede system at the Texas Advanced Supercomputing Center. So this will have InfiniBand FDR with Intel Mike architecture. So we are a partner there, so we are working on the solutions. So by the SC time, you will hear a lot about it for that system. It will be a 10 to 15 petaflop systems. So since we have been working on this project for almost 10 years, we are keeping a very close eye on all the MPI activities. So we support the MPI 2. We are also keeping an eye on the MPI 3, all the features which are coming, I mentioned earlier, and also trying to look at the Exascale and saying that how MVAPICHZ can actually provide supports for all these systems. And this is the kind of like the challenges which are trying to address scalability of million to billion processes, and we focus on highly efficient inter-node and also intra-node communication, taking both the two-sided and one-sided into account, and then also using extremely minimum memory footprint. I'll talk about that a little bit later. And then supporting hybrid programming, how do you balance the inter-node and intra-node communication, how do you provide supports for efficient multi-threading, support for GPUs and accelerators, and especially a lot on the collective side. How do we take the Mellanox collective offload into account, how do we handle non-blocking, topology aware, power aware, and fault tolerance, resiliency, QoS, and then MPI 3. So all those kind of things we keep an eye as we move forward. So what I'll try to do is like go into some of these things. We may not have time to cover all these things, especially here QoS and fault tolerance. I'll not focus. If some of you are interested, I can talk offline. But I'd like to go into some of these issues and then give you some concrete performance numbers and scalability numbers for just you to get a feel of what challenges are out there and how do we really design these components. So first I'll try to focus on high performance and scalable inter-node communication, and then I'll also focus on intra-node communication. So these are some of the latest numbers you will see when we are talking about MPI point-to-point. So how does the numbers look like? And this, we have taken numbers over a lot of different kinds of adapters. This is the MVAPICHZ software stack with the Mellanox and QLogic, and it also has the DDR, QDR, and the latest FDR. This is the ConnectX-3 with PCI Gen 3. So now you will see that this is a small message latency, so it is like 0.99. So we have actually crossed the 1 microsecond barrier. So you can actually do MPI communication from a node to node less than 1 microsecond. And then the right hand side is trying to show the latency versus message size. And here, of course, the FDR with PCI Express Gen 3 delivers the best performance for large message sizes. And with respect to bandwidth, so now we can, this is like a unidirectional bandwidth. So that means from node to node, we are pumping from one node to the other node. And the right hand side is the bidirectional bandwidth, when both the processes are communicating in parallel. So here we are effectively getting like 6.3 gigabytes per second. and then here 11.6 gigabytes per second. And of course, now the next Mellanox has introduced the Connect IB adapter, so we'll be trying to perform some experiments, and then we'll be seeing these numbers are even getting better with it. Now that is only point to point, but once you go into a large scale system, how exactly they communicate. And those of you who are familiar with InfiniBand, it actually provides different kinds of transport. So RC is the reliable connection, UD is the unreliable datagram, then the XRC is the extended RC. So of course, within the MPI, you can take advantage of all these transports, and they have their strengths and weaknesses. So that means RC is good, but then RC also takes a lot of memory, especially when you are going to like 100,000 nodes, 100,000 processes. On the other hand, UD actually takes less memory, but it may not be good performance. So what we have done actually, we have designed a hybrid design. So this I give an example like a hybrid car. You have an electric versus gas, and you want to balance it out. So same thing we do within the MPI library, so that it automatically adjusts. It tries to find out who is communicating with whom. As an user, you don't have to do anything except like trigger some of the parameters, like how at the runtime, and everything else the MPI library is trying to take care. And then if you do that, here it shows some numbers, and here you'll see that the hybrid, which is in the middle, always tries to perform equal or better than the UD and the RC. So it tries to take advantage of both the UD and the RC. And this we had support for MVAPICHZ 1.1 earlier. Now the focus is on the MVAPICHZ 2 since 1.7. It has been there, so you can just trigger it on, and you will really see very good performance and scalability for large scale systems. So here it shows some concrete numbers. For example, HPCC random ring, which is a common benchmark people use. So this is on a 1,000 core system. Here you will see that as the system increases, your hybrid actually gives you almost 30 to 40% benefits compared to RC. Okay. So this is a very easy. So here if you see like what it does, you just, if you want to run like a UD, just use this runtime parameter, or if you want to do hybrid, just use this parameter. That's all you need to trigger on. So especially if you're trying to get some large scale numbers, I'll strongly encourage you to use this kind of hybrid environment to get the best performance and scalability. Now those are with respect to inter-node, but of course the intra-node is also becoming important, because now there are a lot of cores within the node. So when you are running applications, a lot of communication takes place within the node itself. So unless you optimize that, you don't get the performance. And this is one direction we have been working continuously. And here it shows some numbers, like these days we can actually deliver you within the intra-socket. And this is on the Intel Westmere. Intra-socket, we can give you 190 nanoseconds. This is MPI latency from a core to core kind of things. And we also have a kernel module which is called Limit. Some of you might have heard of this. So especially when you're trying to send a large amount of data, you will be able to actually use this limit to get very good performance on bandwidth and also on the bidirectional bandwidth. Now let me go into a little bit and talk about collectives, because this is where a lot of actions lies for large scale systems. So the first is of course called shared memory aware collectives. Now as I mentioned, within the node you have multi-cores, and most of the MPI library these days support like a two-level communication. So that means, let's say you have a lot of cores within the node. As soon as, let's say, think of a broadcast. As soon as I get one copy from the network, I can very easily replicate within the node. I don't have to use very different kinds of algorithms, and that's what we do. So that is called shared memory aware collective. So here you will see this is the number taken from TAC Ranger on 4,000 cores. So the original versus shared memory, you get very big improvement in the performance, and that is also the default in the MVAPICHZ library. You don't have to do anything. Now, more recently, we have introduced this. This is just available in the MVAPICHZ 1.9 release, which we made the release last week. So, in fact, InfiniBand has the hardware multicast. So, how do you really take the hardware multicast into account to get better performance in the collectives? So here it shows like this is on a 1,000 core environment, small message broadcast, you get significant performance benefit, even for the large message also. And more importantly, this is where you see the scalability. Like let's say you are trying to do 16-byte MPI bcast, as you keep on increasing the system size from 32 processes to 1,000 processes, you see the overhead doesn't change that much. And the same thing happens like even for a 64 kilobyte, almost the lines remain constant. And this is what I'll try to again recommend if some of you are using the latest version, turn on this feature. It is not as a part of the default because most of the time when we made the first release, we don't make it default. But over a period of time, we make that as the default. Yes, please.
Is this OFAC only, or does it also support QLogic, Intel, PSF?
No, these are all the OFAC on the Mellanox adapter. Okay, so that's what it supports. Now the next thing which is becoming very big in the collectives is the topology aware. So what does that mean? So let's say you would, as an end designer, you might have designed a collective, but as we know, like any supercomputer center, when you submit a job, so let's say you don't get contiguous allocation. So that means, let's say this job came, they will go get mapped into different places, okay? Because that's what most of the supercomputer centers do. So in this kind of a context, no matter how you have optimized your collectives, when it is really running, it fails apart, okay? So now the question is, can we really dynamically take the topology information into account and make adjustments or make the algorithms adaptive, okay? So depending on every run, no matter where it runs, you should be able to get the performance, and this is what we have done. These are like some of the research study. It has not get pushed into the release yet. We will be trying to do that in the future. Here it shows an example like a broadcast. I can give you like almost like a 14% time improvement for different message size and job size. But now the bigger thing is that not only the collectives, the network process placements also plays a big role. Okay, so let's say on a large scale thing, because like now we are trying to go into a lot of hierarchy on the systems. We have cores within the node, then we have the blades, chassis, then we have the blades, then there is a rack, then the switches. So all these different kinds of hierarchy is taking place. So how do we take that into account to do an effective process placement? So this is a paper actually we will be presenting at SC. This has got the best paper and best student paper finalists. So what we have done is first trying to handle to design this scalable network topology detection service so that it really becomes scalable, it doesn't take a lot of time, and then we try to do the process placement. And here if you see, there is a lot of data here. This we took some numbers on the MILK, which is a common application on Ranger on 2000 core and 1000 core. So here it pictorially shows like Intra-Node. So this is the red. So this is like a 1 hop green, 3 hops, 5 hops, 7 hops. So through effective placement, now you can see this red has increased. So that means more and more processes which were communicating to each other, we have actually automatically placed to run within the node. Okay? So we are effectively increasing that intra-node communication and reducing the other kinds of communication, and that leads to almost like a 15% improvement and application time on a 2000 core. So these are the kind of things we want to really exploit by taking the topology information into account while you are running the job. And then I talked about the non-blocking collectives. Of course, Mellanox has introduced this core direct environment, which is to take the offload. So the hardware actually does the offload. So one is the MPI 3 standard, which is trying to do non-blocking. But then, of course, if the adapter can support it, then you get the most benefits. And so here there have been multiple studies we have done. So here the thing is, once you have the non-blocking collectives, of course the application has to be modified, okay? Because otherwise you don't get the benefits. Your application, you need to rearrange your computation and communication so that you take some computation and then put it in between the collective so that the collective starts and then you get the overlap. So here we have some numbers here like all to all. Here we have taken a P3D FFT, so we get 17% better performance, HPL with around 4.5%. Then here it is a PCG, pre-conjugate gradient with around 22%. And then very recently we took like a non-blocking neighborhood collectives, and there also we see similar kind of benefits. Like here if you see the communication, we are able to reduce in a very significant manner. Okay. So I'll just leave it here. The papers you can actually try to read and then get more details. Now there is also a lot of work going on in the power-aware collectives. As I mentioned, like the Exascale systems, power is a big concern. So here again we have been trying to explore how do you design these collectives so that you get a good trade-off between performance and power. Okay? So here it shows some examples like this is an all-to-all. We are able to do a change in the algorithm itself so that we can deliver you almost like 30% power benefits, but it may affect performance a little bit. Okay, so there is a trade-off here. It's not always like try to give you the best performance in power and performance here. So the next field which is coming is the accelerator, GPU and all. The next talk actually we'll hear a lot, but here let me just tell you what we have been working here, especially if there are very nice animation here. So without earlier, like with the NVIDIA GPUs, everybody does like a CUDA integration. So that means you do a CUDA copy, then you send the data, and then you do a CUDA copy again. So this we call like a high productivity but poor performance. Okay. On the other hand, there have been some very advanced users. What they do is like they do pipelining of data. This is at the user level. So as an end scientist can actually make these copies, and they try to overlap in a non-blocking fashion, do the CUDA copy, then do the CUDA I send, and then I receive. So this is like a high performance but poor productivity. Like the end scientist is spending a lot of time to do this. So what we ask the question saying, can we really do it high productivity with high performance? And that means within the MPI library, if we can take care of this, the end users can only do MPI send, MPI receive. And this is what we have done within the library. So the end users can do MPI send, MPI receive. Okay. And with this, actually we did some studies in the last year at the IC11. So here you will see that this is the kind of number what we showed, which is even better than the user optimized code. And then we did study for all these one-sided collectives and all. Then NVIDIA gave us a grant to take this design and then put it into our software release. So since the last release 1.8, we have supported all this support. And interestingly, if you use these kind of features, you will see that these are some concrete numbers, like we took an LVM, which is an application from TAC, and then there's an AWP. At an application level, we can actually give you 10 to 12% benefits. And this is also on a very small scale system, like an 8-node GPU. Okay? And with more number of nodes, you will be able to effectively get more improvement. And I talked about that Intel mic kind of thing. We are working on the TAC, but a lot of things are under NDA, so I cannot talk into more details. But here it shows some initial design. So we have done optimized, like there are two versions, version 1 and version 2 kind of things, and you will see that we are able to give very good performance benefit with the new version, both for point-to-point and collectives. And let me skip this support 3 RMA because Brian has already showed me the indication. And here we are exactly like MPI 3 RMA model, whatever is available, being supported. We have done the design, so that will be pushed out into the future release. But let me just spend a few minutes on this PGAS. And PGAS especially, there are different kinds of solutions people are doing, OpenSMEM and UPC. So here what we have done is, like we have done actually an integrated. So what we want to do is, the same environment, like this is the OSU design, you can actually run OpenSMEM, you can run MPI, you can also do hybrid, like part of the things you write MPI and part of the things you write in OpenSMEM. So this we made the release last week in the MVAPICHZ. So here it shows some numbers like micro benchmarks like atomic or bcast, collect, reduce. We can give you a lot of performance benefits in the pure OpenSMEM world. But if you want to do hybrid, okay, so there are two applications here. One is a 2D transfer, heat transfer, and Graph 500. So what we have taken is appropriate places in that application, and we see which is regular, that goes through MPI, which is irregular, goes through OpenSMEM. So we take the advantage of both of these, and then you can say here almost like a 45%, 34% end application benefits we have done. And same thing we have done also for MPI plus UPC. So it's a NAS FT, and then this is written with InfiniBand. This is like with the MPI. This is with the UCR, and this is the hybrid. So always you will see the hybrid performs very good, and this is what we'll be pushing out in the next few months into our MVAPICHZ package, X package. So with this, let me try to conclude here. So what I tried to show here, like not only some of the MPI Exascale challenges, but what is coming out in the MPI 3, and especially from the MVAPICHZ side, we are taking a very close look at all these things. And on the GPU, we are closely looking at the GPU Direct RDMA, which is coming next. So we'll be trying to provide support. And a lot of these other kind of things, which is in MPI 3, will be supported. So with this, let me conclude.
Can you just go back one slide? Because it says checkpoint restart, migration support was in memory checkpoint. Can you just elaborate on this? Because You know, that might be extremely important for
So
Exascale.
that's why that part is very heavy, so I didn't cover it because we don't have time. But the broad idea is we have been supporting checkpoint restart and migration for quite a lot of time, but we want to go into the next step, which is called in-memory checkpointing. So that means instead of writing it to the file system, which takes a lot of time, if you can actually write to the memory, and there is a module which is available from Lawrence Livermore called SCR. So this is what exactly we are working with them. So we'll try to integrate SCR with the MVAPICHZ, so that you can do, and it will try to enable you to do application level checkpointing in a much more faster manner. So that's what is the summary, and I can talk offline more on that. So what I did here in the last 45 minutes, just not only presented you an overview of the Exascale, but how the MPI is evolving, especially MPI 3, and how in the MVAPICHZ project, not only we are just trying to support MPI 3, but also keeping an eye on the Exascale, and then trying to handle all the features. So these are all our sponsors, but more importantly, these are all my heroes. All the people in my staff, past and present, they do the hard work. I come here and present. Okay, so the credits go to them. So I always publicly acknowledge them. So with that, I'll be happy to close here, and if you have any quick questions, I can take care of it. Otherwise, I'm here throughout the day, and I'll be happy to answer any additional questions you might have. Thank you.